Section 2 introduced the important concept of the conservation of momentum, and we ended that section with an example, the perfectly inelastic collision. Section 3 wants to focus exclusively on collisions. Certainly the perfectly inelastic collision fits in there, but also there are other types of collisions that can occur as well. Here we have what I like to refer to as the collision continuum, and at the one extreme is the perfectly inelastic collision, and in that case, as we saw, the objects collide and then stick together. At the other extreme is the perfectly elastic collision, and the word perfectly here is in parentheses to show that it's optional. If someone just says elastic collision, that means the same thing as the perfectly elastic collision. I just like the acronym PEC, P-E-C. It's a good contrast to the acronym PIC, P-I-C. In a perfectly elastic collision, the two objects collide, and then they have what we might call the perfect bounce. If you bounce a ball off the floor, for instance, that's a collision between the ball and the earth, and the perfect bounce would have the ball rising all the way back up to its initial position. That doesn't really happen. With real size objects, bounces are never perfect. Perfectly elastic collisions do not exist. However, with atomic size objects, they really do seem to exist. Collisions between electrons, for instance, seem to be perfectly elastic. Anything that's in between is just an inelastic collision. There we go. What distinguishes them, other than sticking together, having the perfect bounce, is that in the perfectly inelastic collision, there is maximal energy loss. Not that the energy is totally lost, but it's probably been converted into a form so that it's left the part of the system that we're looking at. If the objects are moving, we're focusing on kinetic energy. In a perfectly inelastic collision, some of that energy was probably converted into thermal energy. Some of that energy may have gone into crunching or deforming the objects. There is still more than likely going to be some kinetic energy left over after the collision, but it's a maximal energy loss. In the perfect bounce, there is no energy loss. If all of the energy is in the kinetic energy, then however much kinetic energy was in the system before the collision, that'll be the same as the quantity of kinetic energy, the total, after the collision. And in the inelastic collision, it's just a partial energy loss. So energy loss somewhere in between. Only in the perfectly inelastic collision do the objects stick together. So we may want to consider a collision that's not perfectly inelastic. So let's write this one out. We'll have an initial and a final. We'll do this in the one-dimensional case. So we have the objects coming together. In fact, they don't really have to be coming together. It could be, for instance, that object 1 is moving to the right, but it's moving, and object 2 also to the right. But object 1 is going faster, so it's going to overtake it and collide with it. Sort of a rear end collision. Object 1 has velocity v1 initial, or that's the speed, and object 2 is going to be v2 initial. They collide, and then they don't stick together, so they have to move off one way or the other. and I don't really know what they're going to do. So usually I just draw the picture showing that they're both moving off to the right, and then we have to rely on the math, or at least know additional details about the problem, to figure out which way they're really going to move. But the conservation of momentum still applies. Every collision problem is going to make use of the conservation of momentum. Momentum is mass times velocity. So here we can, just to sort of cut to the chase, we'll have the M1 V1x initial, lots of subscripts, plus M2 V2x initial will equal M1 V1x final plus M2 V2x final. And I hope that did it just about right. So we have the conservation of momentum. And given, for instance, the masses and the initial velocities, we can plug that in, but we'll actually find that there's still two unknowns, in which case we need additional information to figure this out. And it may be, if it's just an inelastic collision problem, maybe it'll give us one of those final velocities. Then we have an equation with just a single variable that can be solved. However, in a special case, well, that special case of the perfectly elastic collision, we have a second equation at our disposal. So let's take this. While at the moment, this is perfectly good for any collision where the objects don't stick together. Let's suppose now that we're thinking about the perfectly elastic collision. And it turns out, well, we said it earlier, that if the energy is kinetic before the collision, the energy is going to be kinetic after the collision. The total kinetic energy initial will equal the total kinetic energy final. And we would actually have the conservation of kinetic energy, so another acronym, but I like the COKE acronym. And again, now we're taking this problem and converting it to a perfectly elastic collision example. And with the kinetic energies, we'd have 1/2 M1 V1 initial squared plus 1/2 M2 V2 initial squared would then equal 1/2 M1 V1 final squared plus 1/2 M2 V2 final squared. And in fact, in the kinetic energy, those are the speeds as opposed to the actual velocities. It really doesn't make much difference in the one-dimensional problem, but that's why the subscript x is not included in that equation. And then if we knew the initial velocities, well, we'd also know the initial speeds, and if we knew the masses and substituted in, we would know everything in these two equations except for the final speeds or velocities. Again, in the one-dimensional case, doesn't make too much difference whether you focus on speed or velocity in that kinetic energy equation. But it turns out that only in the one-dimensional, perfectly elastic collision case that you can take the Koch equation, the conservation of kinetic energy, and transform it into something else, much simpler to use. Because it's coming from the Koch equation, I call this one Koch modified. But in fact, it takes the kinetic energy equation and combines it with the conservation of momentum equation. It grinds through some algebra, and it comes up with a new equation that can replace the Koch equation. So we're going to write this one down. And we're going to have, make sure that I write it the right way, the V1x initial minus the V2x initial is going to equal the negative of the V1x final minus V2x final, the negative of that quantity. And this equation, much simpler in form than the kinetic energy equation, can replace it, again in the one-dimensional, perfectly elastic collision case only, but I like to refer to it as Koch modified. The Koch just reminding us that it's replacing the conservation of kinetic energy. But if we wanted to give it a name that fits the equation a little bit better, this would be a relative velocities equation. On the left-hand side, the V1 x initial minus the V2 x initial, that's the velocity of object 1 relative to object 2. On the right-hand side, with this subtraction, that's ignoring the negative part for the moment. That's the velocity of object 1 relative to object 2, except the equation does have the negative of it, so those relative velocities kind of switch around. Anyway, relative velocities equation would be a nice name for this one, but I'm still just going to refer to it as Koch modified. And then to kind of show this clearly, Koch itself, we could use it, but we're not going to work any examples using that one. If you want to enjoy some algebra, help yourselves. Then, with Koch modified at our disposal, we can solve the problem where we have the initial values. So, to just kind of say one more time, go back up to the picture. If I know the masses, and I know the initial velocities, in the perfectly elastic collision case, that's going to be enough information for us to calculate and figure out what the final velocities are going to be. Leads to two equations, two unknowns, so it's not always the most enjoyable one to work through. But I'm going to save that. I've written one up or have recorded some audio to go with it, and that exists out in the examples.